Hello, everyone. This is Stefan from ZKM, and today I'm going to introduce the path towards the real-time proving with the zkMIPS. There are three parts. The first part I would introduce what is the zkMIPS and how we implement the zkMIPS. And the second part I will introduce how we implement the real-time proving with the zkMIPS. And the final part is our use case with the real-time proving enabled zkMIPS. Okay, so yeah, so what is zkMIPS? I think we it's a Ethproofs summit, so we can check out that zkMIPS is one of that zkVM proving the mainnet block on the ethproofs.org. So yeah, I mean one of the different from the SP1, I would say. Okay, so yeah, zkMIPS is really simple and stable because it has about 40 years old history since its first generation of the instruction sets launched. It's about 90, maybe 85, 86. So it's very it's very stable. Actually, it's very has a very established ecosystem. And zkMIPS is the industry's first zk virtual machine supporting the MIPS instruction set. I believe there are some other MIPS-based zkVM, but we are the first one to implement the MIPS 32 and prove the make it be available for you to use production. Okay, and we also have some comprehensive developer toolkits and the proof network. That means the developer can easily use our SDK to generate the proof with our GPU enabled cloud prover. And we also have an integral app protocol. That means we can build the universal settlements across different blockchain ecosystem with the zkMIPS as the infrastructure. Okay, the very typical use case is the God network. I will introduce more about God network in the last parts. So why is MIPS? When everybody I mean, the general purpose zk virtual machine, everybody may using the RISC-V right now. Of course, there's somebody uses Watson, but I believe most of them use RISC-V. But for us, we believe that first, the MIPS is where has a more established ecosystem, no matter for its history or the real production use case. Like optimism, their fraud proof, actually it's already on production, and the underlying virtual machine is the MIPS based. So let's go close to the instruction set itself, and the MIPS basically is the superset of the RISC-V, right? And then we have about basically for the MIPS 32, there are more than 52 instruction OP codes, but we just implement about 52 because it's enough to implement efficient zk virtual machine. And we have native low, higher register. Those kind of registers are special registers, and we have that native supported. But if you are using RISC-V, maybe you need to use like the customized states register to implement on the low or higher register. So, and we also have some special, other instruction like the multiply add or multiply subtraction. So those kind of special, instructions can significantly reduce, decrease the sequence size when we execute the block or any guest program, because it can combine the multiply and the additional subtraction together. So, and we also have some other, more conditional instructions, like the move 0 or move non-zero. Yeah. Okay, so yeah, so regarding the instruction efficiency, basically we are at the beginning, we are not always, more efficiency than the RISC-V. When we, do some benchmark, for example, we have some benchmark on the left table. We can find that RISC-V is more efficient than the MIPS for the SHA-3 chain. So when we dig into this case, we found that the SHA-3 may need the modular OP curve, but SHA-2 doesn't need that. That's why the SHA-3 we are like less efficient. So then we dig into the assembly code, and we found that the MIPS 32 R2 may need about two or three. I would say because there are another TEQ instruction, it's omitted from here because it can be optimized. So we basically need at least two, like the DIV and the MF move from the high. Those two instructions, but for the RISC-32 with the M extension, just need a reminder OP code. But for the MIPS 32 release 6, we have the model again. So that means when we replace backwards the mode instruction from the release 6 to release 2, we can get the same. We can get a better performance instruction efficiency again. So I want to say that it's very easy for us to to improve the instructions efficiency by backwards, maybe adding instructions from the MIPS 32 releases, and because we are a superset of the RISC-V, and then we think that it's hard to actually support the special instruction like the mar add or mar subtraction because it's require introduce new registers. Maybe if the RISC-V supports those kind of instruction, maybe it's not RISC-V anymore. It's maybe become the MIPS. Okay. So that's a very interesting things when we want to improve the instruction efficiency. And for the zkMIPS compiler, we implement the MIPS 32. So regardless of the specific release, and we need to decompose the MIPS program into fine-grained or different chips. And basically the CPU chips become a dispatcher, just gets the instruction and then dispatch the instruction to different sub chips according to their chips type. And then, but one very important factors we need to consider is different chip may. For one segment, different chip may generate different trace table. Okay, so the heads of those tables are quite different. So that means if we want to commit all those tables, we need to in our zkMIPS 0.3, we need to pad all the tables to same heads. It's very inefficient. But on Planck 3, so when we switch to the Planck 3, we can use the MMCs. And it's not the end game. SP1 introduced the jagged PCS, and it's a more better solution for those kind of jagged tables to be improved. And okay, so and for the proof system, the constraint system of the zkMIPS is the PL, that's pre-processed layer, and we use the multi-set hashing as the memory checking and memory consistent checking, and cross table we employ the log up, and for the Planck 3, the quite difference is we are using the corona pair or corona pair. Prime field is different from the SP1 or risk SP1 or some other projects. They use the Poseidon with the baby bear, but we find that the corona bear can can on CPU, at least on CPU they can outperform the baby bear by 21%. Since the Xbox in the Poseidon 2 is quite different. For the Poseidon 2 with the big bear, the Xbox needs a degree of 7, and for Club Bear, it just needs 3. And yeah, and we also need to find the prime the prime extension the extension field based on the Club Bear, and then when we do the hash to map for the hash multi-set hashing, we need also find some secure elliptic curve on that. So that's also part of work when we build the proof system. And we think we have a very good performance after we upgrade from the 0.3 to 1.0. And we also have a benchmark across the different ZK virtual machine, like the RISC-0 and the SP1. We can tell that most of the almost the case we are faster. Yeah, the largest leading efficiency maybe up to 200%. Okay, so all those benchmarks are open source in the zkVM benchmarks and our zkMIPS GitHub organization. Okay, so yeah, so also for our GPU, we like on single NV RTX 1940, we have the province seed bigger than 2.6 megahertz. Yeah, that means we can prove 2.6 mini cycles per second on a single GPU card. And for the for the other components like the proof aggregation and the proof the stack to stack wrapper, we also have a very, very good speed up number here. Okay, so now we have everything we want to run the implement the real-time proving on the Ethereum on the Ethproof, or at least we can do this for our use case like a Go network. Yeah, but the architecture would be similar no matter which use case we are doing the real-time proving. So first we may need to fetch the block, and then we execution block, and then when we execution the block or transactions, we split the transaction, the execution trace into multiple trunks or segments, and then we prove those segments in parallel. And after we implement proof of those segments, we have one proof for one segment, and then we need to aggregate all the proof into a single final proof. The final proof maybe for some case, of course, we need to do some wrapper to get a smaller proof, like the gross 16 proof. Okay, but for the Ethproof, we just need the stack proof finally. And we can see that actually the latency can be defined by the width of the cells, and the cost, maybe the total areas of all the cells. All the cells like the fetch block or execution text, all those rectangles. And yeah, so for different, so right now we can achieve the, finish the proving segments in 3 seconds. And for all the proof aggregation in 3 seconds too. But so that means we have about 6 seconds for the execution phase. So it's so that means if we can see that for each block, I mean, 99% of the blocks may generate about 200 to 500 mega cycles. So that means we actually we need to execute maybe 500 mega cycles per second. Okay, so that means we can execute all the we can generate all the cycles in 1 second, and then we have about 5 seconds to dispatch others. No, not exact dispatch, but we need to ask the different executors to fetch their transaction batch and then run again with the splitted, I mean the virtual machine image, the memory snapshots. Yeah, memory snapshots. Yeah, for each executor, you need to have a snapshot of the executor, and then you fetch the transaction trace, execute the transaction, and then you can go to the proving stage. So basically, yeah, that's what we are doing right now to generate all the witness in less than 6 seconds, and we also have some solution for that. Like we can generate different batch for one block. I mean transaction batch. Yeah, and another solution is maybe we can use some JIT or LT skills to accelerate the executor. And if we have some like the block level access list, maybe it can help for in the future. Okay, so yeah, so that's how we are going to realize the real-time proving. So the timeline for us, I mean, we expected to implement the real-time proving by Q3. It's still on track. And for the execution trace, maybe the parallel execution of the batch transaction is the first priority to do. And we also plan to, I totally agree that open source is very important for ZK virtual machine. So we also plan to open source our GPU implementation by Q4, and the source code will be open source maybe next year Q1. And we also trying to it's we are on the Planck 3 right now, and we also are researching some multilinear PCS meanwhile. Okay, so yeah, I have one use case here. It's about the GOAT network. GOAT network is a Bitcoin layer 2. So basically, the first is it's the first Bitcoin zk wrap with an embedded sustainable BTC yield mechanism, and we need to verify the proof on Bitcoin. So first, so of course it depends on what kind of verification mechanism we are using. There's basically there are different there's 3 different solutions like the BitVM 2 or CloudVM or Delbrag. Delbrag is the gap circuit based solution. So basically we need to generate a proof from a genesis block to current block that includes the boarding transaction of your pegged BTC. So that means it's different from the Ethproofs proving process, because you just need to prove one block in less than 12 seconds. But for us, we need to prove from 0 to current block, maybe more than 100 or 100 mega blocks. So that means we need to, in our solution, we need to prove each block, and then we generate the then we need to aggregate the previous aggregated proof with current block proof to get a new aggregated proof, and then we maybe maybe we need to generate the gross 16 proof for this aggregated proof, because if somebody want to start the reimbursements from layer 2 to layer 1. Okay, so yeah, so this is one of the use case right now, and the testnet has been launched last month. So yeah, and for our vision, we want to build the universal settlements across the different blockchain ecosystem. It's a big vision actually. First step is we build the Bitcoin layer 2 right now. Yeah, and maybe the next step, we are going to build some other, bridgeless bridge to make sure that we can improve the security of the bridging protocol. That means if we have a proof here, we can verify it on any chain, because we generate by a same prover, and we can use it as a certificate that transaction has been done on the source blockchain. Okay, so yeah, that's all today. So for more information, maybe you can check out our medias. Thank you very much.